So good morning, good afternoon, everyone. So I think we should start. So first of all, my name is Wei, and I'm currently employed as a assistant professor at KTH, Royal Institute of Technology. We are also located in this Science for Life laboratory in Sweden. So it's actually I think the second time we present the BioEngine tutorial in this I2K conference. And this year, I'm gonna do this tutorial for you with Jeremy. Jeremy is a research engineer who just joined my lab. And so maybe Jeremy, you can give a quick intro about yourself.
Sure. Hi, Wei, and hello, everyone. As Wei said, I've just joined. Been in the group for a couple of weeks now, and my background is as an image analyst, a computational image analyst, and I'm really excited to have started working with Wei on this really cool project called the BioEngine and the Bioimage IO community, which you're going to learn more about today.
All right, thank you. So I'm gonna switch off my audio, and if you hear anything, let me know. Okay. Yeah, so we two are just sitting each other. It's a bit weird just to switch on the audio. So today I'm gonna mainly introduce you some work we have been done recently. Is a platform for scalable bioimage analysis called BioEngine. And this work is part of the AI for Life consortium supported by EU. And the work has already been, we have been working on this for quite a while with the larger community within the bioimage model zoo, if you heard about it. But I'm gonna talk about it later on. So today we're gonna introduce you this platform. And there will be a kind of intro in the beginning, and then we're gonna move on to the hands-on tutorial. And later I'm gonna share, you don't need anything later on. We're gonna share the link to the slide to you, and then you can open later. But let's just focus on the introduction first, and then within the slides, there will be interactive tutorial where you can work on. So maybe Jeremy, you can send the link, send this link to the chat, and then they can open it later. So I think what we are trying to solve with this new platform called BioEngine is because we are facing a lot of challenges for, especially when involve a lot of AI models for bioimage analysis. Is that for building these kind of different tools, we need to face different challenges in usability. We need, often users expect a user-friendly GUI, and then we need a lot of flexibility because the data type is very kind of versatile. And then when you talk about images, there's a lot of interactivity requirements. And also scalability is a big thing now because we are dealing with terabyte or petabyte of data, often not scale. So, and then there's another additional element when you work with life science is that the privacy. There's a lot of trend in bioimage analysis. Obviously, one of them is to use deep learning. There's also an ongoing trend to move into even larger models. You might have heard this segment anything model, for example, or ChatGPT, which is not directly related to bioimage analysis, but also there's a vision capability gonna be available or already available for ChatGPT, for example, could be used for solving bioimage analysis problems. We are now dealing with a lot of a data set. Previously, deep learning, we kind of exclusively focusing on supervised learning. Now there's more and more self-supervised learning. which you can work with data without any labels, and this kind of virtually increase the amount of data we can use for train models, or what we can work with. There's a lot of other effort, for example, creating ZAR, NGFF, this kind of more scalable file format, which supposed to run on like remote servers. There's a lot of examples showing how you can, store this kind of a large data image volume remotely and make it available through HTTP, S3, this kind of more scalable storage. There's a lot of existing solutions. One of the, classical one is obviously the desktop, like, ImageJ, Deep ImageJ, just a plugin inside ImageJ, which handles deep learning plugins to run deep learning models to analyze images. Elastic, Napari, there's a lot of solution trying to follow up on the progress on AI powered bioimage analysis. There's also notebooks, Colab, Zero Cost for Make, you've heard. Jupyter Notebook has been very popular because this kind of combination of text, note together with the code, and then it's good for educational purposes. There's also a trend trying to enable web-based image analysis. You may have tried, Nucleizer, CellPost, they have this web demo, DeepCell, and EMBL-EBI is just a platform which we have been working on to, use web application to ease the process of deploying of AI solutions. This is kind of a quick summary of the pros and cons of different type of solutions, many desktop-based software and also web applications. On the one hand, if we kind of keep stay in the desktop regime, that you have limited storage, limited compute power locally, and then it's very challenging to install. I think many of you may experience problem if you install Python Conda environment. This is quite tricky. And then it's also hard to share between, collaborators. You need to send large files, and then sometimes you just end up with taking a hard drive or USB disk, to carry around, right? So there are a lot of issues in desktop side can be solved with web applications, right? So on the web, it's especially when it combined with cloud, right? So web typically means inside, things happens inside the browser, right? Which nowadays doesn't necessarily need to connect to a remote server. But when we talk about cloud, it often means that we have access to, either commercial or kind of institutional computing cluster. We can have access to a lot of storage and compute power available in the cloud, either private cloud or public cloud. Often these kind of web applications provide, zero install capability, that you just click a link and then it runs, right? You can also use it with mobile devices, which is great if you can, for example, annotate images on a tablet, right? With this kind of touchscreen, for example, or with a pen. The collaboration becomes much easier if you have a central server and you can just send links around, and then the updates by default is gonna be synchronized easily, right? So much easier than the desktop. So there's a lot of advantages by moving to the web. So one of our efforts previously, which I started a few years ago, is to build this platform called EMBL-EBI. EMBL-EBI is a web application, allows you to build, it's heavily inspired by ImageJ, so you can build plugins to run in the browser. Some of the plugin can run offline without any server, but you just need to open this in the browser, like in Chrome, for example. Optionally, you can also connect to remote engines. Right. Previously, we have Jupyter Notebooks as our compute engine. You can start Jupyter Notebook remotely, and then you can connect to Enjoy, and then you can run computational plugins. Now to bring this effort further to have more complete support on the server side. So we now migrate to this platform supported by Kubernetes. Just briefly, Kubernetes is a kind of software running on the server side, which basically orchestrate a lot of containers. So basically, a lot of services are wrapped inside this virtual machine-like containers, either through a software called Docker, or there are open source alternative like Docker-D, for example. And Kubernetes is basically kind of management or software running on the cluster. It's managed a cluster which allows you to run many containerized services on the server side. So we basically, with this, we kind of also started another track, which is the Bioimage model zoo. So the aim of this is that, besides the effort, we also work on trying to build a model repository to be able to share AI models to the Bioimage analysis community, such that because there's a lot of reasons behind that, having a kind of shared repository, not only, because training is much harder, and then with this kind of repository, you can share models without, retrain, because train models is very difficult. It requires software, complex software setup, complex hardware like GPU, and expertise on, organizing the data. There's a lot of pain on training your own models, right? So having this kind of model repository is good for the user to exchange models, and also for publication, but also for the reason of, because training this kind of AI models consumes a lot of energy and also emit a lot of CO2. It's also environmental friendly kind of platform. So, and this is a kind of screenshot of the model zoo. Feel free to visit the website, bioimage.io. Yeah, let me just do a quick share, on the Bioimage model zoo. So if you go to the Bioimage model zoo, unfortunately, we have some issue in the website since last week because of an API change in the Zenodo platform. So we rely on this Zenodo platform to store our models, but now most of the features should be restored. And then if you experience any issue, we're gonna let us know, and then we're gonna fix it later on. But within the model zoo, you can the idea is that it's a platform where you can find models. You can search for nuclei segmentation, then you can find models. The idea is that you can download the models, and then you can run in different software. We have a list of community partners join us, who gonna, they are mostly software, but sometimes also organization produce models. For example, you have, Elastic, you have DeepImageJ as a plugin in ImageJ to support loading models. But, basically you can download these different models and then run it locally. And, let me get back to the slides. Yeah, feel free to try it out, and then let us know if you have any question. So one of the foundational thing behind this model zoo is that we have been working very hard on creating this kind of model resource description file standard. So it's basically a YAML file standard. Specification defines the fields which we require to describe the model. So why do we want this? Because we want to have a common standard which enables cross software sharing of models. If you train a model, let's say in Python in a notebook, and you want to use it in Elastic or use it in DeepImage, and it's going to be very hard without some kind of common standard which everyone follows, right? So the idea of this model resource description files specification is to define such a kind of additional YAML file which describe how a kind of consumer software can consume this model such that user can use it. And if you go to, I paste the link here. If you go to this website, and then you're gonna find I'm gonna give you a quick overview on what we do here. It's a YAML file, which is text file standard, right? So YAML, very human readable. And then in this specification, we basically define some fields for authors, description, documentation, and the important ones are these inputs and outputs, right? So in the inputs, we basically defines what kind of dimensions, what kind of, when you have an image as input, we describe how should the input image tensor look like, what's the dimension, what's the minimal size of the image, or how many channels, for example. And then we have also output, right? So which is similar, but it defines the what expected from this model if we run it. And then the other important features, like we also have test input, test output, and this allows us to do sanity check on the models. We basically, every model uploaded to the model zoo, we're gonna run the test inputs and outputs, and then we're gonna verify against, so we know that it actually runs, right? So this is kind of important for us for do quality control in the model zoo. And then besides that, we have the weights. Weights basically different type. So instead of having a kind of a common weights format, right, like Onyx does, right? Onyx is a kind of exchange format for models. We don't do that. We just stick with whatever you produce. So we support PyTorch, TensorFlow, Chaos, Onyx. If you have a new format, we can also add it to it. But this is kind of a very lightweight specification. We stick with whatever you have for the your kind of deep learning framework, and then add in additional meta information to help the consumer to consume your models. And yeah, so this is just feel free to take a look. And if you go to the Model Zoo website, and here, if you click this source button, and you can see then how does the model YAML looks like for the Model Zoo. Yeah, let's go back to the slides. And one of the important features we want to provide, because you might have heard there are many other Model Zoo, right? Like there's a PyTorch hub, and there's TensorFlow hub. There's also for transformers, the most famous one is Hugging Face, right? So but most of those Model Zoo, they are targeting developers. So here we are actually targeting non-expert users, like biologists, researchers who has no experience in programming, for example. That's why it's important for us to support this test run feature. So the test run is basically allows you to run the model in the browser within the Model Zoo website with your own images without any download or installation. So you can just try it, go to the website, and so for every model, so for every model, for example, we have animal names because it's a zoo, right? So this kind of affable shark, this is kind of my favorite model. So if you scroll down in the web page, and then you can test the model, and then you can load the model. Let's see. So this will basically, what we are doing here is that it allows you to load an image, right? And then you say run the model, yeah? So what happens is that if you load this image, it's load this example image, and then this image is gonna be send to the server and then provide you this example output, right? So you can try other models. Most of the models should work, but there are some exceptional cases we were currently working on to fix it. And we also support 3D sometimes, right? And feel free to try it. So this is kind of the test run feature. So the way it works is that we read an image. You can also try with your own image, but it's a bit harder because you need to feed them, each model has different requirements on the image, on the input data. So we are trying to improve what we can provide, but for now, you need to, crop or resize the image according to the requirement of each model, right? If you've done that, and then you can load your own image to try it with the model zoo. There's an ongoing effort trying to support, for example, you provide an image, then we're gonna screen a lot of models within the model zoo and show you a gallery of results. Then you can help you to pick a model which you like, for example. So this works because it's mostly because we put a lot of effort on building the underlying cloud infrastructure to support this kind of test run feature. And under the hood, we actually use this BioEngine, which is the main thing we're going to talk about. It's a computational platform or framework for allow us to load models to run it on the server side. So in a nutshell, it's a set of Docker containers running on the server side, but the server can also be a workstation. Sometimes it can also be a laptop. So for now, what you need to aware is that the BioEngine is a set of Docker containers. It will load all the models from the model zoo. So we have a public model zoo with all the models. And then inside the server, we use this called Triton Inference Server, which is a tool from NVIDIA. It's a kind of framework. It's another Docker container which load the models, and then it will listen to the request from the user, and then it will run it. So the advantage of this Triton Inference Server is that it allows us to dynamically schedule model execution, especially when you have only a few GPUs. In a project like this, a platform like this, we cannot afford, for example, hundreds of GPUs, right? We can only have a few GPUs provided for free, but the models can be a huge number, right? For now, we have less than 100 models, but once we get the project, move on, there's more and more models get contributed to the model zoo, and then we're gonna have a problem, right? How can you serve hundreds of models on a single server with a few GPU, right? There's a lot of challenges and how to scheduling, how to load and unload model efficiently, how to serve a lot of users simultaneously. So this is actually the problem we try to solve within the BioEngine. So our solution is to use this Triton Inference Server. Besides this, the Triton Inference Server, we also developed this HiFi, which is extension. Is kind of the main idea behind HiFi is kind of extension of EMBL-EBI, which runs in the browser. Now we kind of implement the similar idea of this remote procedure course to run on the server side. So HiFi is a communication hub, allows us to manage Triton Inference Server. But in addition, we have other components in the form of Docker containers and connect to HiFi such that we have a kind of a platform which allows us to orchestrate different services on the server side. And this is how it works under the hood, right? And then, but for the users, is kind of what we are trying to achieve is that we provide the API for different software to connect to, such that you don't need to manage. The advantage of this is that, for example, if you develop an Apari plugin, which runs on top of the BioEngine API, you don't need to worry about the dependencies anymore because you just send the data to the server and then it returns the result. And you don't care about what is TensorFlow, PyTorch, or anything. The same apply for, Elastic, Deep Image, and then we have also some. So these software tools, we started to support this and talk to the API, right? And the request can be either as simple as an HTTP request sent to the server, or you can get a bit more powerful if you talk to a WebSocket based API. So we have also other because the main computation is done within the BioEngine on the server side, and the client becomes much easier, right? The client can be just a web browser because we don't need any heavy computation anyway, right? So, and this makes EMBL-EBI much easier to handle this kind of heavy computation, especially AI-based image analysis. We also trying to support Jupyter Lite, which is a web version of Jupyter Notebooks, which you don't need to do any installation. You just open the link. I'm going to show you later on. So later on, the tutorial will be based on Jupyter Lite, which you don't need to install at all. One of the bigger ambition of the BioEngine is not to just work, serve as a kind of public free model execution service. We also want to serve the BioEngine. We want to provide the BioEngine as a deployment toolkit, which you can install in your own lab, in your own institution. And also you can replicate the setup we have in the bioimage model zoo to your own institution. It can be, you can collaborate with the for example, in your institutional IT to have the same Kubernetes-based installation. So you don't need to send data to our server, or you can, and you will have your data directly, attached to the BioEngine, the instance you install. Then you don't need to upload data, for example, right? And then in a small scale deployment, we also support Docker Compose based instead of a Kubernetes. You can set up your own BioEngine on your, for example, a workstation in your lab, or in some cases, you can also install it on your own laptop, and you can just do one command, Docker Compose up, and then you will have BioEngine running in your own kind of laptop or workstation, for example. So this is the development is still ongoing. We don't have kind of deployment toolkit yet, but just for your information, now we want to just make it public and then let everyone to test it in the community, provide us feedback, and then we can improve the service, and then later on we can provide you a better deployment toolkit so we can share to make this kind of bioimage analysis more scalable. These are just feature highlights of BioEngine. BioEngine trying to handle many models is perfect for you for a project like AI for Life, like the bioimage model zoo, where we want to serve a lot of models. It's also for serve many users. It's not like a Jupyter Notebook solution. If you start a Jupyter Notebook, if you want to mount a GPU, right, and then a single user gonna occupy a GPU the whole time. So this is not scalable at all. If you want to make GPU, especially you cannot provide this kind of service for free. But in our case, because many models, many users are sharing the same a few GPUs, and we are much more scalable in terms of that. And we also, in addition, which we don't talk about in this tutorial, but the BioEngine actually comes with much more powerful than just running models. We also allow deploying applications and manage data, for example. This allows you to work with many applications. And in the meantime, many applications also means that with your own client software and Apari DPMJ, you can connect to the BioEngine, and then you can develop your own software workflows, which is more flexible. So as I said, it's shared with many GPU resources. If the one of the important features that we try to work with limited GPUs. So the GPUs are shared among many models and many users. We also trying to support training. The major features on inference. The one released is mainly on inference, but later on we're gonna support training. I'm gonna provide some more example later on. We can also support local or cloud deployment. So you can also try to install later if we provide the deployment toolkit, and then you can have your own on-prem deployment. So let's move on to the hands-on tutorial. And this is gonna be, you will do it with Jeremy. Yeah, so does everyone get notebooks or?
Yeah, and also the slides. So
okay. Yeah, so please make sure you click the link in the chat. And if possible, if you have a Chrome, and use Chrome or Firefox to make sure, I'm not sure what, because we didn't test with other browsers. Yeah, so we're gonna do copy, yeah. So I will let Jeremy to do this tutorial with you.
okay, cool. Right. So, okay. Hello, everyone. So yeah, so I'm just going to walk you through the tutorial. Partly that's because I only recently did this tutorial myself. So this is a refresher for me as well as being something hopefully new for you. Right. So if we switch to so hopefully everyone's on the slides that I've linked to in the chat. If you scroll forward, so about halfway through the slides, you'll get to the tutorial 1. And you should all see this screen. And if you click on the click Start the Notebook button, with any luck, fingers crossed, this will happen. And you'll see a nice browser-based JupyterLab session running. So this is kind of this Pyodide-based JupyterLab Lite that Wei talked about. And all we're going to do is just run through this notebook, which is going to give us a nice overview of using the BioEngine, but from a Python environment. Obviously, this is kind of like a Python Lite environment because it's running in the browser. But for those of you who want to, this is also something you could download and try and run offline later on. So let's get started. So as you can see, this is written to run both on.
I think you will need to reset. I think my browser cached.
You've cached it. Yeah.
So, sorry about this.
Yeah.
There
you go. So yeah, that's a good reminder for anyone who kind of does anything in the notebook that they don't like. If you scroll up to the top of the page, this slide, you can always press the reset button, and that just refreshes to a kind of basic version of the notebook again with no changes. Okay, so first thing we're going to do is run this first cell, and as you can see, it's written for both the desktop and the browser, because it'll either run some code that will use micropip, which is the browser-based version of pip, or it'll run native pip. Hopefully that all just runs, and that helps us to import both Hypha's RPC, remote procedure call, as well as some utility functions from Kaibu, which I think Wei might talk about later. And the first thing we're going to do is run straightforward UNet or reasonably straightforward UNet segmentation model. So we're going to use remote data that's also hosted on Zenodo. So you can see the URL there. Unfortunately, Zenodo recently changed their API. So you kind of have to look partway through the URL to see that this is actually an image file. But if you run this cell, you'll see that it pulls down this nice EM segment through a nerve, I think. And yeah, so first thing we're going to want to do once we've managed to pull this image down is connect to the Hypha server. So to do that, we're actually using these utility functions called connector server, which came down from the ImJoy RPC module. And we're using, at the moment, today we're using the server URL of ai.imjoy.io. That might change in the future, in which, so kind of we'll keep you posted as to that URL to use. But for now, we're using that. So if you run that cell, hopefully you'll find that the Triton variable gets populated. And the very first thing that we want to do once that does work is take a look at this RDF that Wei mentioned. So the RDF is our description of what a model does. So probably the easiest and most straightforward way of figuring out what a model does is to actually go onto the bioimage.io site. BioModelZoo site. But because obviously if you look at what we're actually running here in the next cell, we get a model ID that's Creative Panda. That's good for, it's kind of good for identifying the model from a kind of fun, unique perspective, but it doesn't tell us much about what it does. So by examining the RDF, which is the YAML file specification of that model, and printing that, we'll actually see more information about that model. So the inputs, the outputs, and any other metadata that the authors of the model have added to that entry.
It looks like we have.
Yeah, we might
can check. Does it work for everyone?
Is anyone else managing to get stuff running? Because I think what's happening at the moment is we've probably all been pressing. We've probably all been running these cells, and
yes. In case that you have a problem, you just reload. Restart the kernel. You will need to restart the kernel.
Yeah, we can't. It's got what a timeout of 3000, is it?
Yes.
Okay. So yeah, sorry for anyone who's experiencing issues with that running at the moment. That's basically just because we're all trying to run it at the same time.
I can restart the kernel.
But yeah, we'll just restart the kernel. It works. So some of you might have gone ahead. It's running on my side now. And if you run the Triton.execute, which is the main kind of interface function at the moment, you can see a bunch of metadata that's come down. The important ones are in the inputs and outputs, which I'm scanning through now. Somewhere in there's inputs. So that's the test information. Data types, yeah, and it gives you a bunch of keyword arguments as well. So this information is the same as what's present on the ModelZoo website. It's probably easier to actually use the ModelZoo website at the moment to find this information. But if you kind of need to verify in your code which model you're actually working with, do this and just scan to make sure that you're working with the right model. There we go. So and this, as Wei mentioned, some of the important stuff that you're going to get is things like the output and the input. Here we can see, for example, that we've got an output of 1.5.12.1. And that's going to help a lot when you start trying to run data that isn't the test data. So this all works well with the test data, because test data is formatted in the correct way. But as Wei mentioned, once you try and run data that's not in the correct format, this will help you a lot in terms of knowing, okay, well, now I need to reformat the data to fit this specification. So we downloaded this image a few minutes ago, and now we're going to try and run some inference. So basically segmentation on that. And it's worked. So that was nice and quick. It's output the data in this 4D shape that it said it would, which we can now display. And then we end up with a nice standard kind of prediction mask for the segmentation on this EM image. So if anyone's having issues with that, please let us know in the chat, and we'll try and help you with that. So the next thing we're going to do is just work on another model or two. Some things to bear in mind. Obviously, some of these steps can be shortened or abbreviated into functions. We haven't done that at the moment, but it's hopefully that's not something that you're not familiar with. So
should we do some time for the break?
No? What time is it?
45.
Yes. Okay. So as we've just finished the first example in the notebook, let's just take a 10-minute break, 5-minute break, 10-minute break. All right, let's take a 10-minute break and meet back in 10 minutes. Cheers.
Sorry, I forgot.
Oh, that's okay. Switch over to the bioimage.io website, and then we can type in the ID of the model. So in this case, it's Creative Panda. That leads us to this card here. And if you click on that, you get a bunch of information, like a nice summary of what this thing does. This example page actually shows you that the membrane is going to come out as, well, in this image, black with this color map. So that's a good verification that it's doing what it's supposed to be doing. But on top of that, you get a bunch of additional information.
Hold on. So I think there's something. This one is not moving. Screen share is not moving. Is that right?
Oh, you didn't resume. Yes, we didn't resume. Sorry, we didn't resume share. Okay, sorry everyone. I think we forgot to resume the share there. So so let me just show you that again. You might have heard me talking about what I was doing, but you probably didn't see what I was doing. So let's go back. So close this down, get rid of that. Right. Okay. So what I was trying to show you there is just that from the ID that we have in the that we gave as an input here to the execution. We can basically go to the bioimage model zoo, and how do I exit that again?
Sorry,
that's okay. Yeah. And if we go to the Bioimage IO, so the model zoo.
Hold on, let me just do like this.
Yes, that would. Cool.
Cool. Yeah.
We can type in the ID of the model that we were just looking at. And what I was pointing out is that actually, if you open up that model, so you click on this little card for Creative Panda, the first thing you see actually is an image that verifies that in this case, the model's output is actually going to show the membrane as class 0 and a non-membrane as class 1. On top of that, it's a much more pleasant way of seeing the same information that's in the YAML file. So you can scroll through, and this is also where you can test the model with test data. Okay, so this is a really useful resource, because what you can do then is, once you have your own data, you can type in, for example, what type of data you have, and hopefully this will then be able to find you a list of corresponding models that you can use on that data. Right. Okay, so let's get back to the second example. So this time we've actually done everything in a single cell, and what we're doing is we're going to fetch an image of some nuclei, and we're going to run it using Fearless Crab. So just to check what Fearless Crab's going to do. Fearless Crab is Stardist, and it's a fluorescence nuclei detection. And what we're going to see there is, let's run that. So what we're going to see there is a nice sample image of some fluorescent nuclei. And in just a few seconds, the predicted mask. Now, in this case, the prediction is actually quite a large array. So you can see it's not just a single image; it's actually essentially a Z stack with 33 layers. Now, the reason for this is that post-processing hasn't been done. If you want to, as kind of offline example, try this out on a local notebook. You can test out the Stardist library and use that to do the post-processing on this model output. That's not something that's part of the of this model yet, but we are working on incorporating those pre and post processing steps into the BioEngine. Okay, so hopefully that gives you a good overview of a few different models that you can run. Let's just do one more to finish off this first tutorial, or this first exercise of the tutorial. This is going to be running some HPA single cell classification. Now, for this one, if you pay attention, you'll probably see that we're going to be using a slightly older interface. So this time the model name is, we're not actually giving the ID, and that's just because the server actually has a really nice model already kind of present that we're going to use here, but very soon we're hoping to have this be part of the model zoo as well. Right now, we're just going to run standard class prediction, and we can see, so we have this nice image of the cell, and the model is able to correctly predict that that's cytosol. Great. Okay, so I think we might have missed out on some questions at the end of the first section too. So if anyone has any questions, should we take those now? Either feel free to ask in the chat, or if anyone wants to ask any questions, that's also fine. Yeah.
Sorry that we are switching Zoom.
Yeah.
Okay, so is there any question? Let's see. Did you manage to run this models in the notebook? If yes, could you raise your hand, for example, just to get a feedback, get some idea whether you have successfully run the models. Yeah, clap one. Only one.
Yeah.
Okay, cool.
If
Nice.
anyone else wants any help with that, feel free to chat. Yes, so Stardust blocked. So the blocking might be due to it might just be due to a lot of people trying to run it. What you can do is restart the notebook as Wei explained earlier.
Yeah, try it later. So we have, because right now the server we are serving you for this tutorial, it's a single workstation with only one GPU. That explains why. But we currently trying to deploy this to a more like larger Kubernetes cluster, and that hopefully gonna be serve more users. Yeah, you can try it, and maybe a different time, send notebook and send API, and then as Jeremy also mentioned that there might be some changes we're gonna make, but I would suggest you. Sorry. Any question? There's no. Sorry, I have to mute you. Shout out if you have some questions. So I'm gonna actually show you how to. Let us send the link, the BioEngine link, so they can BioEngine. Yeah, so we have a GitHub repository. I'm gonna post it in the chat. So keep an eye on this. If you follow or watch this repository, we're gonna have updated material about the BioEngine. Is there other question? Any question? Otherwise, I'm gonna move on to the second tutorial, which is gonna show you if you click the link here, yeah. So if you click this button, and then you can go to the next one. If you go back, yeah, this is kind of the previous tutorial. So I'm gonna show you briefly how you can use this BioEngine. Because right now in the first tutorial, the notebook which we have been showing you is mostly accessed from the notebook. And actually we hope that this API, if you are a developer of a tool or bioimage analyst, which creates some sort of tool or notebook, we hope you can try to use the BioEngine to integrate into your workflow. So here in this notebook, we're gonna show you how we can actually integrate with the GUI, right? So in this case, we show you with a image viewer called Kaibu. Kaibu is an Android plugin. If you open kaibu.org, and then this is the viewer, we have a nice drawing tools. For example, you can draw, and yeah, we have a lot of different ROI, and you can even cut the ROI, for example, and then you can break this into two parts, right? So feel free to play with this tool. This tool is it's a bit still ongoing development, but why the name Kaibu? You can see this, right? So it's actually quite, Kaibu is actually another island in Fiji. And And then we named this as Kaibu because of Fiji, but also because of Napari. And this is an image viewer we built for for the web, for the Enjoy ecosystem, but you can also use it as a kind of a native, standalone. And we have, if you click the documentation API here, you can see how you can actually interact with the viewer. If you work with Napari, and then this kind of some of the API is actually quite close, right? So here you can also interactively try this. For example, this is how we do Enjoy plugins, right? If you this is the Kaibu plugin. This is how we kind of use this plugin, and then you can interact with this Kaibu plugin. For example, in this case, we just view an image, we pass the URL, and then you can see this image here. There's a lot of other examples which you can directly try in the web page. For example, here you can also create some custom input form, allows you to do image annotation. You can see the code here. It's kind of quite customizable, right? So it's Kaibu by itself. It doesn't do a lot, but the idea is that you can use it as a kind of reusable component. You get a view object, and then you can change the display. Like you can view image, and then you're gonna add a layer. You can add a few images if you want. You can also add shapes, similar to Napari, right? So then you can also add this kind of widget. The widget is the thing showing on the left here, right? So in this case, we just add a few widget to allows you to annotate this image. In this case, it's a kind of skin cancer image, which you can annotate. You can also, if you want, you can make a kind of nice app, web app, allows you to draw, right? So this Kaibu also works on mobile phone. If you open kaibu.org on mobile phone, it also works. It also works with, obviously tablet. If you, we put a lot of effort trying to support this kind of join. So going back to the tutorial, right? So here, what we show is to, similar to the previous example, we just define this function here. You can see it's quite familiar with the previous tutorial. You have this Triton.execute, right? So you pass the image and then some parameter. So in this case, we use another model called CellPose. CellPose is a very nice model for segmentation. It's also a so-called generalist model where you don't need to retrain in most of cases. We wrap a function called CellPose segment. We fetch an image from this remote human protein atlas. And then we resize it such that it will fit into CellPose. And then we run the model. Yeah, so this is just to fetch the image. This is, we print the shape, right? And then you can do CellPose segmentation. So you can see how it looks like, right? So the segmentation, you can set the diameter too, right? So it's quite fast and without setting up anything on your local. Keep in mind, this notebook is just within the browser, right? We don't set up any server or notebook or Jupyter Notebook server. It entirely runs in the browser. What happens is that the Python code running inside your browser, and then it sends the request to the BioEngine server. And this is what you see. So in this tutorial, I'm going to show you how you can make a quick application with the Enjoy plugin. So as we see the BioEngine API, the Kaibu API, right? So you can use this viewer.view image. You can control what to display, and then you can interact with them, the viewer. So let's walk through quickly about the code here. So because we have this Enjoy integrated inside this Jupyter notebook, you can then create an Enjoy plugin, and then you can create a window to use this Kaibu plugin. Then you can view the image, you pass the image. This is a NumPy array, right? And then you view the image. Then the image will be shown here, right? So this is what you are seeing. So now we define a function, say do segmentation. And this, which will be used in this widget. So here we add a very simple widget. It's add with a button. So we just add a button here, right? Say do widget. The label is do segmentation. And then once it's clicked, and there will be a callback function, be called, which is this one, right? And then let's see what we do here. We run this cell pose segmentation, cell pose segment, which is the same one we tried here, right? And then we convert, it will return with a mask, which is another image. With the image, you can mask to feature. This is a function we provide in the Kaibu utils, right? So you can see where we import this, we import from Kaibu utils. This allows us to convert the mask image to GeoJSON format. So this polygons is actually in GeoJSON format. And then the viewer will take GeoJSON to display the polygons, which we produce. So let's see, if I run it again, and then if I click do segmentation. So what happens is that it will send the image to the server. It returns a mask, and then it can do mask to feature, right? So you can, and then the viewer gonna display these polygons. Yeah, it has the name called prediction. You can see that here you have a prediction. So you can see this is actually not an image, it's editable polygons. Where you can, edit, you can remove it, for example, right? So this actually allows you to, like, for example, you can add more. So you can modify it and place it inside a kind of interactive annotation workflow, right? So we're going to show you something later, but this is just something allows you to, make a quick application, right? So you can just change the image, and you just need to find a way to load your image, right? So here we just took the example image. I guess in your own Jupyter notebook, you can just load your own image. And then maybe you can add another button to go to the next one. Let's say in Python, you can easily make a kind of tool for image annotation or image segmentation, where you can say, okay, next, to go through a list of files locally. And then for each one of them, you can click do annotation. If there are some of them doesn't work well, right? And then you just remove them and redo it manually, right? So this kind of application could be useful, maybe for you. And then feel free to take this notebook as a basis to, create more. So you can also easily think of, this is just for Enjoy plugins, which you might prefer other tools, for example, but the key part is the same, right? The key part is this cell pose segment. So if you want to, try something else, we're gonna put up a bit more links trying to follow this BioEngine repository. We're gonna maybe add more, more examples where you can develop more powerful GUI-based applications later on. Yeah. Is there any question for this part? You can either type it in the chat or, just unmute yourself and shout it out. Oh, yeah. So we should move on then. over there. Good. Yeah, so if you click then, yeah, I think you don't need to. You can, feel free to work with the data model of your choice. And, as Jeremy also, told you that BioEngine is meant to be, generic. So you can find a lot of models in the model zoo, and then you can try with the ID in the first notebook. If you want to build some nicer integration, try the second notebook, second tutorial where you can, enhance it, or either try things yourself. Cool. So I'm gonna wrap it up with some, I'm gonna show you some comparison with other tools, and also I'm gonna show you what we have been working on as a preview feature to you, which are not available yet, but you can also try it, and then you know what to expect in the coming months, for example. So one obvious comparison is how do you compare BioEngine versus Jupyter Notebook Colab, right? So the key difference is the scalability. If you're talking about serving models with limited resources, right? And then BioEngine is the choice. It's much better than Jupyter Notebook and Colab, which is more computational. Let's say the resource heavier, mainly because when you open a Jupyter Notebook, right, it occupies a GPU the whole time when the user opens it. If you want to serve many users, then that becomes a problem, right? So BioEngine is really designed for this kind of cloud and on-premise deployment. Is for multiple users or for the public. And you can also think of as a kind of internal service within your institution or lab, where you have many users and trying to run many models. Yeah, so we want to make it as a kind of multi-model serving framework, improve the GPU utilization. So it can, in our case, actually during our tutorial, we only have one GPU, and then we are actually allowing running this kind of notebooks for many users, right? So although there are some kind of issues, of course, there's no way that you can serve many users simultaneously. But if you can queue them, let them use, it's not a problem. BioEngine is also, we aim to relieve the pain of setting up the dependencies, right? With Jupyter Notebook and Colab, it's gonna be a bit harder. Although you can also use the container environment to make it easier. But the idea of BioEngine is meant for this kind of case, you have this running and up and running without worrying about the dependencies. So you don't need to set up and install, you just interact within your tool. Please stay tuned. And as I mentioned, that there's a new few features under development. We are currently working on, for example, have this kind of deployment toolkit where you can deploy your own BioEngine under a Kubernetes cluster or your own workstation. And Jeremy is also gonna work on, we have been discussing that having this nicer installer where you can have a nice GUI where you can configure the BioEngine to select which model to install, and ideally on your own laptop, right? So you can download, install, and then pop up a GUI, say, okay, I want to spin up a BioEngine with this list of selected models, for example. And then you can connect with your own other software, right? PG, a web app to locally, right? So entirely locally. So you're gonna have BioEngine on your laptop or another workstation, which you can configure through a GUI and then run through other applications, right? There's also a training service which is under development. I'm gonna show you But, feel free to, follow this BioEngine repository. We're going to keep all the update, a new feature available there. If you have a GitHub account, watch that repository. We're going to make updates there. I'm going to quickly show you the kind of some preview feature we are working on. One of them is these training models. I'm going to show you how it looks like, right? Let's see. So here, what we are doing is to, we want to train a cell pulse model. So the idea is that we would like to, within the BioEngine, we want to provide a public free service for users to upload a few images or, some images with labels like, input image predicts mask. This is actually the ground truth mask in this case. And then you can upload this to our server, and then the BioEngine gonna train a model for you, and then you download. This is the idea. So here I'm gonna show you how it looks like, right? So here you can create this kind of application where you can say, I want to train this model. I give a name. This is a kind of number of ID. It can be just a new number, right? So then you can see the training progress. And multiple users can train at the same time too, in our server. So here we just train for 10 epoch, and then you can predict. Let's see how good are we in terms of time. So we are good. Let's wait a bit. So here we're gonna run this 10 epoch of training. Let's go back. So while it's training, I'm gonna go back to show you how it looks like. So in the train function, we pass a batch of input and labels pair of, it's a number array, right? And then we run a for loop. In the for loop, we just call the BioEngine to train. And then each time when it's run a step of training in the BioEngine, it will return some information, including the loss. So this is how you see the loss value, right? So basically, you can think of the BioEngine takes this kind of training step on the server side, giving you the rest of it on in your notebook. So that's why within this kind of browser-based notebook, browser-based Python, we can do training for cell pulse model, right? This is kind of cell pulse model. So this is a preview, mostly because we might want to change the API later on to make it easier for developers to use it. But for now, just take it as a kind of preview feature where you can look into. So the idea is that this train function gonna run for 10 epochs. Each time it's gonna send a batch of images to the server, and then the BioEngine will, train this particular model with a number as ID, right? And then it's gonna train. So you can see now it runs for 10 epoch because we set 10 epoch. And then you have the predict, try this model. If you set the same ID, then it will use the model. So notice that the model is entirely on the server. So we never download or anything. It's just exists on the model available as under this ID, right? And then if you want to download the model, you can just set this ID and then you can download. So this is an example that we just download the model and then it will be automatically packaged in the Bioimage model zoo compatible format. As you can see here, this is the model. You can also download, you can right click and download. This is just another ImageOi plugin we use to display the file. So here you can just download, then you're gonna see a pop-up. Okay, so yeah, I think here you can just use it to run for more models, right? See how it looks. Notice that, this model is not perfect, right? Because we just trained for 10 epochs. And then if we set pre-trained model to none, so actually this model doesn't start with it's a cell pulse model training from scratch, using only a few images and then train for only 10 epochs. And then it's be able to achieve this kind of performance, which is already good. I mean, many of the other models doesn't work like this. Cell pulse, I think, is actually very good in terms of working with very little annotated data, right? So yeah, I mean, here you have some issue, but considering it's a new model training from scratch, just with a few epochs in a very short time, right? Okay, so this is one demo. Any question for this? There's some chat, huh?
Oh, yeah.
So let's look at some of the questions. Do we need to see some of the interesting ones? So I see that there's a question about any plan for including microsam. Yes, actually last week we have been in this hackathon with AI for Life consortium. Konstantin, who is the author, the team of the leading team of microsam, we actually worked on one of the small project to deploy microsam to the server. However, because we are currently limited on the GPU resources on our local server, hopefully we will have it soon, to available in the BioEngine. We already converted the microsam, the encoder, decoder, already in the BioEngine compatible format. We have been tested locally, but it's just not there yet. It's mostly because of a computational. Excuse me. Okay. In the future, when you deploy your own BioEngine server locally, how much is modular? Actually, all those gonna be packaged into Docker containers, right? So, you just need if you have a Docker installed on your workstation or laptop, you just need a single command, right? Docker compose up, and then you're gonna have all the component ready. So it's gonna actually quite modular. So you don't need to touch on many of the things. There will be some kind of configuration file, which we aim to provide this BioEngine installer, which is a graphical interface to generate this configuration file. And then Docker Compose is gonna take this configuration file and then spin up the component accordingly. Is there other question? There's another one. When you talk about on-premise deployment, what are the prerequisites? Full installation of BioEngine, how to install all the dependency. So actually it's much easier because BioEngine, as I mentioned, is just a set of Docker container. If you have a Docker, then you don't need to worry at all about any of the dependency. Although if you want to use GPU, obviously you will need to install the CUDA, not CUDA, but the GPU driver. And then the CUDA and everything gonna be handled inside the Docker container. So the minimal dependency is a kind of the easiest if you deploy it on a workstation is to have a GPU and then have a kind of Linux system like Ubuntu. That's the easiest. We can still support Windows and other machines, but then you need to get Docker installed. If you have these things there, and then it should be easy. Just do Docker Compose up. If you have a more like a large-scale cluster with Kubernetes, that's even easier. we have a kind of package called Helm Chat, right? So Helm Chat is the kind of a similar to pip package for Python. Helm Chat is for Kubernetes. So you can do a Helm install, this kind of a command. So we are working on that. Yeah, so if obviously there's a lot of interest in like local installation, please keep an eye on this GitHub repository I provided. Cool. Is there other question? All right, so let's move on. Yeah, I'm gonna show you another notebook. So in this other notebook, what I'm gonna show you is that some kind of very preliminary. It's built on top of the training feature. I just want to show you what we can do with this. It's just with this kind of BioEngine supporting training, you can do interactive annotation, right? So this is just a quick notebook, allows you to actually. Okay, so there's something wrong with this. Okay, sorry. I think I will need to patch it. There's a piece of code which I didn't, I forgot to put inside. Sorry. It's this one. Okay. So this is the model training. I'm gonna show you. So this is only needed for this browser-based Python environment. This will be fixed. Otherwise, we'll need to skip. Yeah, so we have a few example in this function, right? So you have train ones. You can see that how we can support training. The same example you see before. So, and then we have this, I fetch one image as example. And then this is just a quick demo, see how you can run the inference, right? So, so you can see that we have this train once function, which allows you to train the model for one image, right? This image is this image, the mask is this one, and we want to train the model for a small step. Okay, so 106 is broken. We need to switch to 108, which is the same one as we did before. So we're gonna train one step. Again, 106 is broken. Switch to 108. So 108 is just another model, right? So it's 108 is the one we used in the previous step. And then now this is the important part. Let me make sure that we already changed this 106 to 108. Yeah, so this is a similar example as we did before, right? We did do segmentation in the previous notebook. Now we can do, I'm gonna just show you how it looks like, right? So you can say make prediction. Oops. Let me see. Let's see. Let me see if I can fix it now. Let's see. Ooh. Do prediction, predict model ID, image to feature. Okay, so it looks like we have some issue with this notebook. Predict 108 reload, and then we have the ask. Let me do another quick try and see if it works. So there's something wrong. Okay, so for the sake of time, I'm gonna leave this part, but the idea is we will be able to, the idea is to show you that we can do first make prediction, then it will generate automatically this kind of annotation as you see in the previous notebook, right? And then the idea is you can modify the polygon generated by the model, and then you can send it for training. So this is just a quick example. Actually, we have a more complete example if you want to see. It's here. Let me see. 1000. So we have this. I'm gonna send this link to you. So there's a video here in the chat. You can do interactive annotation, which is the same idea as a backup. So the training feature is still under development. That explains why we are kind of still a bit buggy in this kind of process. But the inference should be stable and ready to use. So feel free to try that. This is just a quick demo that shows you that, you can modify, you can do prediction first with the model, which can be a very kind of preliminary model with a lot of errors. But the idea is that you're gonna fix it manually and then send it back for training. So this is kind of a way to show you how this could work, right? So here I'm kind of splitting cells. Let me see if the previous frames should be like, okay, so we select another image. We click predict. Predict will run this model once, right? And then the model gonna propose a result. Yeah, you can see that it's not good, right? So it's kind of, these cells are merged together. So now we kind of use this cut tool to cut into pieces. And then there's a missing cells. We can just, add. We've kind of fixed it, right? So still, this is faster than you can annotate from scratch. And it's more targeted, you are kind of providing ground truth in the place where the model tends to make mistake. And this is actually more efficient than you kind of annotate everything, Okay, yeah, and then you can click the button, say send it for training. And then you can see it will take this new annotation, then train further, and then, do this. So this is kind of a work in progress. I just want to show you how it looks like. Oh, sorry, click the wrong button. All right, so yeah, I think I hope you get an idea on how it looks like, and this is just some ongoing, some work ongoing, and then if you want, there's also, I'm going to show you a few examples more that we actually working on, having this kind of BioEngine integrated with other software. In this case, it's IC. Carlos is the one behind this work. They are trying to interact with the BioEngine, so you can use it from IC, which is a Java-based program. Right? This is also cool because you don't need to, get into the mess of embedding Python inside Java, for example. And this here, you just make some kind of HTTP request from Java, and then you have access to all the models. You can think of BioEngine as the public service where, a kind of software like IC can interact with. Or you can also be the case that you install a BioEngine locally on premise, right? And then this make it more interesting because in your institute or in your lab, you can use IC with BioEngine. There's another thing which I made previously, is AI assisted Bioimage. It's basically ChatGPT. We call it Codex before. Feel free to take a look at this video too. Yeah, I think that's mostly it. I hope you now know how to use BioEngine, and feel free to try it. And also, yeah, and then we have this notebook provided. Feel free to try it more, and then if you have any questions, let us know. Feel free to reach out. Yeah, just some acknowledgement. So this work has been carried out with at the cell profiling group. In my previous lab, ImJoy has been done by a lot of people. The Biomodel Zoo as well is kind of a consortium work from, with a lot of effort from many teams. So I would like to also thank the founder. AI for Life Consortium is actually supported by the EU. It's a research infrastructure grant to support this work, mainly supported by the EU, the BioEngine. Thank you. So is there any other question? No? Okay. Okay. Thank you. Well, then, yeah, let's, thanks a lot for joining. And if you have any question offline, if you want to try later, and then let us know, and then, yeah, just contact us in the GitHub issue, or send us emails.